data in real time, you're just not going to be able to do it.
Yeah.
So, you use DMA, you can take 10,000 samples really fast, store them into some sort of memory, and then take them out of that and do like a Fourier transform or something on them so that you analyze the data in some way, not in real time. So this is a way of basically, it allows the microcontroller to
Be very
do things
efficient.
very quickly and efficiently, and possibly do things in bursts where it can't necessarily process everything, but you want some sort of something to happen very quickly. So queue it for later.
And this is like a good example is how good is your sound card in your laptop. It's either completely done in software or it's done via hardware using DMA. And you're either, your sound gets funky when your computer gets loaded, or your sound always sounds fine. Maybe this is like 15 years ago and nobody noticed this happens. But yeah.
All right, so in addition to DMA, there are things that are called events, which are kind of similar to interrupts. But they're interrupts basically for DMA. Like an event might trigger a DMA, might trigger a memory access to start transferring. Or an event might be, I'm done transferring. I've got to 6,000 samples and you told me to stop at 6,000.
Programmable trigger might be a good name for an event. So great examples of what you do is you set up a timer to overflow. So let's say you want to sample something at exactly 8 kilohertz, which if you've done like a digital sampling class, that usually really starts you off as 8 kilohertz sampling. So you say, okay, my timer's going to flow at 8 kilohertz. And then you create an event that says, when this thing overflows, the ADC should start and convert. And so you could then, and then the CPU wakes up when the ADC is done. So every 8 kilohertz, an ADC sample is just magically starting. And like that sounds useful as opposed to like just starting whenever it feels like. Or trying to figure out like, okay, I'm just going to constantly sample and then guess which one is the one I want. Or you might want to have your UART captures data from the GPS. And then you want an SPI to write it to the SD card. But you can do these very complicated things. So UART gets data. DMA slurps it away based on that event. And then the SPI, it gets data, so then it automatically sends it to SD. And then when needed, the CPU can wake up to like do a page write or page load or whatever it has to be done. So suddenly this stuff gets very fast, and then your code can be furiously working hard on blinking lights to make cool colors or whatever your code has to be doing. Whereas like the hard work is being done automatically.
So application notes. If you go to the product card, so each of these have like a...
Yeah, so do you see how tall that page is? Like that scroll bar, we're kind of at the top of the page. Here's the data sheet. What's all this stuff? And it just keeps going and going and going. And what Atmel does is, for some reason, they really want people to use their chips, so they try to make it as easy as possible. And what they do is they give you some things. So like, hey, would you like to use the DMA controller? Here's an application note. And what they actually do is there's a PDF that explains what's happening, and then there's a little zip file where they give you code that just compiles on an Xmega and does exactly what they tell you it does. So like the ADC, do you want to just find one for like ADC?
Yeah, so
or iSquared C?
Here's the DMA.
I think iSquared, something that's like more sensible.
Well, how about serial? We're going to use that.
Yeah, serial is good.
So...
I'm going to search for serial. There are a lot of them.
Yeah, so basically you may have to do something like this. Serial, and I don't want serial memories. I want Xmega USART.
Xmega USART. So would you like code that just makes your 18 Xmega USART work?
All right.
Answer is probably yes.
So in here they have 3 ways of using a USART, serial port. One is through polling, so you're basically, your CPU in your main loop, you're saying, hey, have I got something yet? Have I got a character on my serial port yet? If so, do something. Yeah, question?
I have one note about this sample code though. I was using it a few months ago, and one thing I learned is that a lot of the sample code is written for, I believe, the Intel compiler for the AVR, which is an expensive compiler, and it won't necessarily work with AVR GCC.
Usually,
There's this AVR compiler.h file that if
Okay.
you include it, it seems to
yeah,
work.
you include it and it lunges the munching bits.
Okay. There was
Um,
one that I found for an AT-Tiny that I couldn't get.
It depends on how old the code is too. Their XMega stuff is all pretty new and good.
Okay.
Their 18 mega stuff
Yeah,
is not as good.
that's totally true.
Probably
Now, I guess what we're also telling you is that for Gadget 2, you're welcome to go find drivers and use them in your code. We're more interested in gadgets than making you guys poke all the registers from scratch again. So, go ahead and find things like, these USART drivers. What I'll tell you is that they're usually pretty mediocre in terms of implementation, but they work. And sometimes a mediocre implementation you don't have to put any effort into.
Oh, yeah.
That can be nice.
Most of the time.
They're not efficient in any way.
Yeah.
But if you say, gee, I really want to save some bytes to EEPROM and then load them up later, like, you can do that. It's the same kind of register poking. You'll end up with a couple functions with a couple lines of code. Or you can just go find the EEPROM driver for XMega and you're done.
Or you can take the EEPROM driver, take the parts you want, maybe change the code a little bit to make it more efficient, and you're done.
Yeah, and
You don't have to start from scratch.
And I'm pretty sure, I don't know a specific one, but like all these example code probably works, but you may still have to understand what's going on, figure out why it doesn't work in your case.
And I mean,
Maybe a configuration, maybe a buggy example.
for understanding what's going on, obviously each zip file comes with a PDF.
Yeah, I would read the PDF first and then figure out what to do. It turns out that Atmel has a lot of these. They have for XMega, they may have them for Tiny and Mega, but maybe not. I'm not sure. I just
I
trust them.
wouldn't trust, yeah, I wouldn't use those. So yeah, I mean, they're giving you like example code for how to use the serial port, not just with polling, but also if you want to use it with interrupts instead, or if you want to use EMA to, take the serial data and just quickly shuffle it somewhere. So there's a bunch of approaches basically to how you read data from a serial port, and which one you do is pretty much whatever is appropriate for your application. So yeah, the app notes are very, very useful. They are sort of, in Arduino land, like Pross was showing, they have all these, fairly nicely laid out functions all ready for you. So you have just your put byte and get byte or whatever, and it's done. The app notes are
Basically.
kind of analogous, but definitely hairier and not as easy to work with because they're not just integrated into the compiler. You don't just have immediate access, you have to include the file.
But what you'll see there is right away they give you, with the Arduino, you get to use the polling-based approach for serial. That's what you get. Whereas Atmel said, well, here's the polling approach. It's kind of terrible, but it's the easiest way to understand the code. Oh, by the way, here's the interrupt-based one that will automatically fill a buffer for you. And oh, in case you want that buffer to be filled with no CPU intervention, here's the right way, the DMA approach. It's like they're giving you the various sophisticated ways, and then you can integrate them into your setup. Whereas Arduino, right, it works right off the bat, but then does not work any better, put more effort into it.
Alright, so reference schematics. We've created reference schematics, Eagle schematics that you can use for the ATmega 168 and the XMega 3284. So if you want to just have like a skeleton where the parts are well defined, or if you want to, take that and copy the parts out into your own schematic, that's perfectly fine. Arduino, obviously, you can just download from their website. So this is our way of making it slightly easier, given that with the Arduino you just get it.
Yeah, you're also welcome to use the AT-Tiny
Yeah.
skeleton from Gadget 1
Yeah.
for Gadget 2.
So long as you can justify that you're using a digital interface on it.
Yeah, good luck.
Which, yeah, it's possible. If you use SPI, it's not too bad. Okay, so we're going to do a live demo of XMega coding, just so you get an idea, and we're going to do it using a serial interface on. This is a BrainLink, and it has Bluetooth over serial, so it's just going to connect to my computer over Bluetooth, but it'll look like standard serial. It has a module in it that just converts regular TTL serial signals to Bluetooth. And then on the computer side, it shows up as a serial port. So I've got WinAVR open, Programmer's Notepad. Let me make first let me pull the make file, which I think will, or let me make a new place to put the code. So let's make a folder called XMega serial test. I did this last night, so I have all the code here. Okay, and let's get a make file. Put that in there. That's just the standard make file for Brainlink to program and data on. So like I said, we're using serial. I want to just use, I'm not interested in rewriting all the serial code from scratch, so I'm just going to use the AppNote driver that Atmel provides. So, that's in this download. And I need usartdriver.h and .c, those look good. And like I said before, you also need the AVR compiler.h file, because that's referenced by usartdriver.h. All right, if I go into polling control, I can take a look at their example code, and maybe that'll help me get started. So that's task 1. And I'm going to make a very simple thing, which is just a serial interface to blink the LED, turn it on and off on the Brainlink. So, polling is just fine for my application. So let's look at task 1. This I didn't actually look at last night, but I'm sure it's going to be fine. All right, so there's board.h, which we don't need because that's just defined for, I think, like a...
That would be your
Next
mini
step.
gadget.h,
Yeah.
that sort of thing. Where are your pins? Where are your LEDs?
Okay, so they have an LED port. They're this is kind of a terrible way to set it, but, and they have a buffer. That's kind of funny. They're not really setting stuff the way I would expect them. So I'm just gonna close this, make my own. Okay, I'm gonna make a C file. I need to include usart driver.h. And I need int main void.
Do you need AVR?
Yes. So that's just the overall, like AVRIO.h just tells the compiler with the information from the make file that this is an XMega 32 that, basically maps all the pins, maps all the registers.
Yeah. You want to know what port B is, you have to ask AVRIO.
Okay, I'm gonna make some defines for my LED port, which is port B, I think. And then my LED pins, I'm gonna have to look that up. I'm just gonna open my cheat sheet from last night because there's a lot of crap to remember.
Miscellaneous.
So here we go. I'll just. Yeah. So it's a tricolor LED. There are LEDs on pin D0, pin D2, and pin D1. Can everybody see the text okay, or should I try to make it bigger?
Close that bracket.
This?
No, the thing.
Really?
Yes. Okay.
Okay. I'm going to create a 8-bit variable, a character called data, which I will just use to read in characters from the serial port. And then I'm going to set my LED port to be LED port.dear set. So I'm setting these as outputs, or equals red LED or green LED or blue LED.
the nice thing about Durset is that Durset never actually saves any information, so he can do that. And then if next time he wants to do
Yeah, I don't
some
know.
other pin, he just or equals, yeah.
Can just do that.
Like, there is no, Durset, you can't actually read it, it doesn't mean anything. It's just like, they created a hardware macro to sort of make it just, the code a little bit nicer.
So now I'm going to go into my usart driver.h file, because this is where all the functions are. And basically reading this file is how I know what I need to use. So the first thing I need to do is I need to set up my serial port with a bunch of parameters. So, you know, it's a lot of stuff.
Sometimes
I
this
don't
is where
want
you look at the,
Okay, so they've called it usart format set. And they kind of tell you, yeah, they do have, I think there is documentation like that you can auto-create with this to make it look a little bit better. But they have 4 parameters. There's the pointer to the module. There's the character size, which I think is just 8. Parity mode, which I think in this case is no parity, and then 2 stop bits. We don't want 2 stop bits. We don't want 1. So I believe I need to do a usart format set. So I'm going to reference, I think, usart D1, which is the serial port on port D, but it's the second one, so it's D1, because the first one is D0. Let me just check if that's right. Yeah. Okay. And then look, all right, so,
where did all that magic come from?
yeah, look at all this. Let me copy these over and explain, because I wouldn't have remembered these either. So usart underscore ch size underscore 8-bit underscore gc basically is a group configuration bit that just sets the usart character size, so the size of each blob of data, to 8 bits on the serial port. Usart p mode disabled means that parity mode is disabled.
So what's really nice about these is once you figure out what they're called in the compiler,
Yeah.
like retroactive is like, oh yeah, that does make it clear what's going on. But then you have to figure out where to find it. And usually all I do is I find that .h file and I search for things that sound about right.
So on my computer, it's going to be found in C drive, WinAVR, AVR, include, AVR, and then under here, IOX, I think 32A4. All right, so if we open that,
It's long.
yeah, it's
So you
very
just
long.
search for like,
So,
like
okay, there's too much
character size.
stuff here. So I would look for usart, and I would keep looking.
F3 maybe? 5,
Okay, so there's a lot of these. So let me just get out of this section, keep going. Okay, this looks like a promising section. So here's a bunch of structs. Like if you wanted, you know, here's the control A register. So you might remember the control A register from random different register modules like ABC, control A, or whatever. Here's the way to access it. Character size. Here it is. And look, it just maps to some random, you know, X value.
So we get really sad if we see
No.
just do 0x03.
Here's parity mode. So you can use disabled, even, or odd.
And hey, look, it supports Erda on the user. That's nice.
Okay,
These
so
things really can do just about anything you can imagine.
so we've set the baud, we've set the format. Oh, let me. Yeah, okay, that's fine. Now let's set the baud rate. So there's a baud rate set. And unfortunately, the way to set it is not like, let's say you want 115, 200. there's a calculation you need to do, which gives you kind of two values. It gives you a select value and a scale factor value. I've already done that calculation, so I know what they are. So what I need to do is I set USART D1, and then if I want a baud rate of 115/200, then I can use these two values. So yeah, I know those came out of nowhere. There's somewhere on Atmel's site is actually a spreadsheet where you can look up where you can ask for a baud rate, and it'll give you these values with the minimum % error given your processor speed.
For older 18 megas and 18 tinies, it's a much simpler calculation. So either Atmel literally gives it to you in the data sheet, or people have like macros that just do baud rate set. But 18x megas are really cool in that they do fractional baud rate generation, and you can actually like do different divisors to get closer and closer to true baud rates. It'd be a lot more flexible. The downside is that it's more complicated. So you could write a baud rate set function, but they don't just give you one. Yeah, I have no idea why.
Okay, one thing I've forgotten to do is I want to set the TX pin to output, and I know that the TX pin, let me just declare it. Now define TX is pin 7, and now define RX is pin 6. So I need to also set this out to, and then for the RX pin, I want to be an input because it's reading data in, so I want to use dear clear.
In this case, the default pin IO control stuff is fine. You could do funny stuff.
And then you also need to enable them as serial port pins. And so that's something in the driver. So notice enable USART receiver. Because you could actually just enable the receiver and not the transmitter. If you just want to listen and never want to say anything, then you just enable the receiver. So that's USART RX, so that's receive enable. And I only have to give it, I don't have to give this one anything else, I just have to give it which port I'm using.
And the application note has all this in gory details.
Yes.
What is it like?
I will check. All right.
And what you can also do is, you could just steal their example code and modify it to fit your intent.
Yeah.
Probably a little clearer if we do not just hack, copy, paste code. That's so much.
Brian really needs his practice code. Okay, so how do we get data from the serial port? There's if you look, there's a little bit further down, put char and get char. Okay, now it's tempting to just do data equals USART get char, and then this USART D1. The problem is that if you just do this, this is going to run like nonstop basically, and any value that's in that buffer, if it's in the buffer, it's just going to keep giving it to you. Instead, probably what you want to do if you're polling is you want to wait until you get data and then read it once and then wait again until you get more data. So the way to do that is there's a function called isRxComplete. So is receive complete. This basically just checks, is that the right one to use?
Is there a key
Check.
here?
Yeah. So what you can do is you can make a while loop that as long as Rx is not complete, it just hangs out in the while loop and does nothing at all. So you can see how this is horribly inefficient because you're just burning all this time just checking this over and over again. And this is why interrupt-based methods are usually better.
This is the equivalent in like C code of KB hit
Is
on like
RX.
a regular computer. there is get C, there's put C, and there's KD hit, where you're like, did anyone hit the button on the keyboard? If so, we want to be careful, otherwise we don't read it.
So in this loop, we're gonna wait until we've gotten some data, we've gotten a chunk, a byte of data, then we're gonna read it in. I like to transmit it out again so that you can see, especially when I'm just testing, I like to just see that it's actually receiving and that I'm transmitting. So the first, if I've just written a serial program, the first thing I do is I have one where I get data and then send the same data back just to make sure it's working.
So a remote echo program, basically.
So there it is. So you start ClipChar to you start D1 and then send out data. Yeah. So I'm going to save this by, and because my make file is already configured to compile things with the name of main firmware, I'm just going to call it main firmware. It's really lazy.
Back. These are lectures.
All right, main firmware.save. Tell me what mistakes I made. Okay.
Sorry, complete. So what's it actually
What's
called?
the declaration?
So what's it actually called?
Yeah, so I made a mistake in how I called it. Is RX probably just
RX is both.
RX is capitalized. So the X is capitalized. Okay, I'm going to set this in bootloader mode. So this has a bootloader. What that means is, unlike your mini gadgets, it doesn't require an ISP. It has a little program that hangs out way at the top of its memory stack, and it checks if one of the pins is grounded on boot. And if so, this is like the equivalent of having a button pushed down on boot. If so, it goes into a bootloader mode. And the bootloader basically allows the rest of the program, once it's in that mode, any data that comes in over serial, it says, this is program data, I'm gonna make a program out of this, and I'm gonna reprogram the flash memory. So that's what it's doing. It's in bootloader mode now. Bootloader mode is indicated by a blue LED. And so when I hit Tools, Make Program, if I've configured the COM port correctly, and if everything's working, it will flash the LED while programming. All right. So now it's in regular mode, and the LED is actually on. It's kind of hard to tell because it's just green, but the red one is on and the blue one's on. They're just dimmer. Because this LED is inverted, and when I set those all to outputs, they were default low, and so all the LEDs turned off. But that's okay. It's minor. Let's just check if the serial is working. So I use a terminal program called RealTerm, which is freeware.
You're in Windows, you want RealTerm.
RealTerm is nice. You have a lot of options. So I set the baud rate to 115.2. Oops. Abort scan. And I know that I'm on port 45. So if I open it, it takes a little while because it's Bluetooth. If I type R, G, so I'm just sending data, and it is sending it back to me. So yay, my program's working.
Go to display,
Right.
just check local echoes. What's that?
I think there's a local echo somewhere, but I know.
Probably that.
The nice thing about RealTerm is you can send in like hex. You don't have to. You can also look in hex. So if you ever want to find out what the code for lowercase g is 67.
Yeah, it's much better. Honestly, I like it better than a lot of Linux options. And if you're on a Mac, well, you can get a virtual machine and run RealTerm. It's pretty nice. And this, hasn't been updated in years, but it just is very flexible. And let's say your baud calculations were wrong and you just can't figure it out. This will actually let you just be like, you know what, I want 112,000. You just can type it in, and as long as your hardware supports it, it'll do it. And you get a lot more flexibility over this stuff. Whereas Hyperterminal, first it wants to know your area code for some reason, and then you get your 4 choices of baud rate, and you have no choices other than that. So RealTerm is very flexible. The only way to get more flexibility is to actually write your own serial terminal program, at least that I've seen.
Do you want to do the mini gadget?
Sure.
Because we got 10 minutes, so
Yeah.
I'm not gonna.
All right, so that is, you want to just find the code.
Yeah.
So just in the interest of showing you some other stuff, we're also going to give you, so that's just the Atmel code that Tom downloaded. He obviously wrote a little bit of code, but if you copied their first example, it would work the same. For those of you who are sticking with the AT-Tiny, just open the bladder.c.
So yeah, if you want to stick with the AT-Tiny, not even the AT-Mega, but the Tiny, or if you want to make your current gadget or your mini gadget have a serial port.
This is how you can do it. It's actually a lot more complicated than it looks. I don't think, for instance, we actually need sleep. I don't think we need atomic, standard lib, or string. Just what ends up happening when I'm writing code is I have all this stuff, and I just keep adding these header files. They usually don't harm you to leave them in, but then we delete a bunch of functionality, for example, and we just sort of stick it. So if you look into AVR libc, which is, you just Google it and look at it, it has a lot of functionality. So for instance, if you would like something like printf, you can have it. You just have to set up a stream. And this ends up looking a lot like what you do on like a Linux computer. They explain it in gory detail. What you have to do is you have to give it a way to send characters, and then if you want to, you send them a way to receive characters. Here, since I'm only writing, I've only done the add char. But if you did set up read write, you could also send and receive. It's pretty straightforward. And then what you have is we have the main function, and then I'm just initializing a software UR. Here I do standard out equals my standard out. If I just called this standard out, printf would work. So printf will always print to standard out. But I could have also done this. Let's see. And that will also work. So there are these sort of basically library support to give you things like on a regular computer, like printf, the string library, like it has a whole bunch of that sort of old crufty C stuff that it's convenient. But basically all this is going to do is printf, banana, and then delay. So we could have done this exact same thing. If all of this was hiding out in a library.c and .h, you'd never see it. If this was in something called, a function called setup, you'd never see it. We have another thing called the loop here, right? You can make this look very pretty if you wanted. Maybe change the fonts on programmers notepad to be blue. But basically that's all there is to it. What's actually going on, if you're curious, is we've got software.c and .h. Where all we've done is, here we define some pins. So if, for instance, you want to have your software on different pins, that's fine, just change them. Here we've got a baud rate. This is software UART. It's on a slow microcontroller, so you're not going to get 115, 200. I think you can go up to 38, 400, but slow is good. If you wanted to have more software UART, so you could have more. And then what we're doing is there's a get char, a put char, there's add char, print string, KB hit that's very handy for do I have any data in my buffers. And then what actually is happening is we're using a timer. So instead of doing it to Blink Software PWM, we set up a timer at around 9600 baud, and we just look and see, is there data on my serial port? And if there is data, let's see, let's go find the timer function. So if the serial port has no data on it, we're just hanging out, but then we suddenly see data, then we're gonna start, capturing the bits. And we start at mask, we start at the first bit, and then we just keep capturing bits until we're up to the stop mask, which I think is 10. And then once we get to the stop mask, if we get a stop mask, then we're gonna push our 8 bits of actual data into a buffer. And same thing with the transmit. If we actually have something to transmit, and that transmit happens to be high, then we output a high on that pin. Otherwise, we output low, and then we just keep shifting through the bits on this buffer until we're out of bits.
So this is actually, what this is doing is, because your ATtiny doesn't really have a hardware serial port, or it has sort of a pseudo one, this is doing in code what a lot of the hardware would be doing automatically on an X Mega or even on an AT Mega. So that's why it's so complicated and why there's all this bit shifting, and why you can only go at 38 to 400 bits per second.
Now, there actually is a serial port on your ATtiny. It's the USART, it's also used for SPI. This is really handy if, for instance, you wanted to talk SPI to your accelerometer or something else, but then you say, well, gee, what would make my life 100 times easier is if for development, for debugging this thing, I can talk to it and figure out what's going on. So that what you could do is like, okay, every time my gadget turns on, it'll send something to the serial port. And then like you're working on it, you're doing some code, you're like, every time I do this, it resets. And I know it reset because it's telling me over the serial port that it just reset. And this is sort of, this is the printf style of debugging, which is, a couple orders below JTAG style debugging, but it's still better than nothing.
So even if you didn't intentionally put this on, it's likely to be on your ISP header, and unless you've overloaded those pins, you probably just have it.
Yeah. So
even on your gadget.
So for Gadget 1, you guys could use this code, plug in these pins. You just put the TX and RX to your MISO and MOSI pins, and you should be able to have like a little mini UART to talk to yourself. And it'll help you a lot. Like let's say you're getting a sensor value, and you're trying to figure out whether you should have a red unhappy LED or a blue, happy LED, and you don't know whether a value on your sensor resistor of 170 or 62 is the right value. It might make your life a lot easier to just read in the analog value,